Okay, so in the previous part, we talked about how we can find some roots. And now this is the section for 10b. We're going to talk a little bit about iteration. So we're going to build on what we did last time with a few extra steps. So the first thing is we're going to get a function, and we need to show that the function being equal to 0, which remember is when you have roots, can be written as this. So all we need to do is we need to identify that there are multiple x's in the function, and we need to find the right one to get on its own. So I noticed that there's a natural log, which I know is the inverse of e. So let's try and get that x value on its own. Okay, so let's start doing that. So I'm going to do 0 equals e to the x minus 1 plus x minus 6. I'm going to start to get the e bit on its own, because you want e on its own before you apply natural logs. So let's do 6 minus x equals e to the x minus 1. We'll do natural log of 6 minus x equals x minus 1. And then we will just add the 1 across. So we will do x equals natural log of 6 minus x plus 1. Okay, so that's that one there. And I think we're now going to have a look at the next bit. So notice here it's the same as before, but we have some subscript. So this means the next term, this means the term before, and this is a starting value. So it's an iterative process. An iterative process is when you start with something, you get an output, and then that output will be your new input. So you would have done this at GCSE a little bit. What it looks like is kind of using ANS on your calculator quite a lot. So let's just show you how you would find x1. So the formal way of writing it would be as follows. You would say x1 equals the natural log of 6 minus x, which we just showed, plus 1, and that's your x0. So the idea is that you would put in here your first value, which is 2. So if you do x1 and you type all of that into your calculator, just find where my answers are. I've got them somewhere. So I get x1 is 2.386 and so on. And then when I want to find x2, what I would do is I would take this answer and put it in instead of my 2. Okay, so this would be my new way of doing it. And I could just keep doing that again and again and again. It works really, really well if you change this part here after the first time, change it to ANS on your calculator. It speeds up the process a lot. You'll get that x2 is equal to a fairly similar number, so 2.2847, and then we'll do one more. X3 ends up being 2.3125. So what you should notice after a little while is it's gone from 2 to this, so that's almost 0.4, and now it's changed by about 0.1, and now it's changed by 0.03, so it seems to be slowing down. And in the language of iteration, we would say this is converging on the value. Okay, so we've done that one there. C, this one here, that's what we actually did in the previous lesson. So the idea is that you would do 2.3075 and you would do 2.3065 in the original function. You would get a change of sign, of sign or in sign, a change of sign. You'd write your typical conclusion. Okay, so I'm not going to go over that one in this video. So let's just have a look at this one here, and we'll have a go. So a starting question that you might want to think about is, does the starting value of x matter? Well, we're going to see with some diagrams, some staircase and some cobweb diagrams in a moment that it does. Also, I've seen this on papers before. There are multiple roots. So you can give them names. So the first root, instead of calling it x, you can call it alpha. The next value for x, you can call it beta, and so on and so on. So sometimes the question will ask you about this, but you actually end up finding the other one. Or other times, and you're going to see this in a moment, things diverge. They don't slow down, and it's to do with the shape of the functions that you've got. So let's have a go at this one here then. So it says, here's our function, show that f equals 0 has a root in this interval. Okay, so 3 and 4, going into this, change in sign. You know the drill by now. You should be pretty confident to answer that. So apparently we get a -1 and a 13. It's a change in sign, it's continuous, so there's a root. Okay, exactly what we want to say. Use this iterative formula. So we don't have to show it always. Here it's just use. So if we really wanted to, if we got that x there on its own, I can tell it's that x there because it's squared, and this is a square root, not a cube root. So if we got that x squared on its own, we could turn it into this iterative formula. And it wants us to start, to find a first, a second, and a third approximation. That's what that means. Starting at 1.5, starting at 4. So I'd recommend you pause the video here and have a quick go for yourself, and then I'm going to talk through what happens. So what you should find is the first one, these numbers, notice that they seem to be slowing down. So this is convergent, okay? What happens with the other one, though, is you seem to be getting values where it's sort of exploding. Okay, or it's diverging, you would say. It is divergent, so the iteration has failed. So this must have something to do with these starting values, because it was the same function both times. It was just depending on whether we started at 1.5 or 4. So just before we go too much further, pause this video and have a quick go for yourself. It's got the part A that we started with at the start of this video, part B using the formula, and part C is really a throwback to the first video, okay? But hopefully you can see how this all ties together. So the idea is, this is a question, it seems to be about alpha being between 1 and 2, and it looks like when we do the formula, we should get a number very close to this. And it's created by starting with a value of 1 with this version of iterating this. Okay, so there are different ways that we could do it. It's always set equal to 0 because it's fundamentally about finding roots. That's what we're doing. So assuming you've had a go for yourself now, the show that, we just want step by step always with show that, please, and make sure that it matches exactly as it is on the final line. Okay, so that means you need the x equals element on the left as well. Okay, with the values, you should have found that you got 1.41, something, so AWRT, this is, you'll see this a lot in mark schemes, it means answers which round to. So you can be more specific, it just needs to round to this. So that's why sometimes you may see me in these videos write things like, 1.4123, okay? Yeah, because we care about what it rounds to, rather than saying, oh, it must be one decimal place or something. And finally, at the end there, this is that question where we add and subtract, change in sign. Notice here that it doesn't mention continuous, but my big bugbear is that you do need to say it in the new spec, please. It is not optional. Okay, so let's start getting on to why some things work and why they don't, and how to use the diagrams, because yes, you are expected to know how to use these. So I'm going to just kind of talk through to start with. So we're always going to have this red line here, which is our y equals x line. I'll talk about why we need that in a minute. And the blue line here, which this time is given by this, depends on the original function. Okay, so because we rearrange this to x equals root x plus 1, that's why the blue line is root x plus 1. This line will always be this line. So let me show you how it works. Do I have a starting value? So this, this is what we are trying to find, okay? This is a representation of the root of this, where this line and this line cross here, that will be a solution to the original equation. So we're going to do some reasoning by starting at 1, okay? So where does this come from? This comes from the question. So what we do is, this is our input, and we go up to the blue line and we get our value. So what would we normally do here? We would normally say, okay, what's the value? It seems like it's about 1.4, yeah? So what we're then going to do is we use 1.4, don't we, as our next number that we put into this blue line. So 1.4 is about here somewhere. But instead of doing it like this and doing that and then getting a better value, which seems to be about 1.5 or something, instead of going up from there, what we do on these diagrams is we go across, because we know that that's the value that we will end up using anyway. Okay, so you always go vertical, then horizontal, and then what do we do next? We will go vertical again, and horizontal, and vertical and horizontal. Okay, so it's perpendicular, vertical, horizontal, and so on and so on and so on. And you'll find here, this is a staircase, okay? You'll find here that it will zigzag its way across. So what you're doing is the same as like doing this, but it's just much quicker, okay? So let me just show you the neat version. So up, across, up, across, up, across. Sometimes it might be down, across, always vertical, then horizontal. And you can see that it seems to be converging on this value. So we would say this is a successful iteration. Here's another one. So this is going to be a cobweb diagram. So we can see here that this is the value that we should get, which should solve this equation. It's been rearranged for us already. We've got the interesting line of this one here, and we have the y equals x line that we always have. We're going to start over here this time. So what will happen? So I'll talk you through, then I'll show the animation. So we get our value from the interesting line, which seems to be here about, well, what is this? Seems to be about minus 0.3, something like that. So what could we do here? Well, couldn't we? We could take our x1 here, and then we could do the same thing again. But to speed this up a little bit, what we're going to do is we'll just go across there. So we do our vertical, our horizontal. Where do you think we should go now? Have a think about it. So it's going to be down here. So we're going to go vertical until we hit the other line. What should we do there? Well, we'll go horizontal until the other line, and vertical, and horizontal, and vertical. Okay, and so on and so on. So do you see, it seems like I'm kind of convergent on that value there, which is exactly what's going on. So here's the neat version. Okay, so this also converges. This is a cobweb diagram. It tells us that we shouldn't be scared that things are kind of yo-yoing between more positive, then negative, then more positive. What we're interested in is seeing that the gaps are slowing down, and eventually it should stop changing. So if you had values like this, what would be going on? Well, it would be a staircase divergence. It's a staircase because they go in the same direction, and it's a divergence because, look, the number's not slowing down. Next, how about this one? Looking at the numbers, they just go up. They seem to be slowing down. Eventually, your calculator won't change the display because you're converging on the value, which is very, very close to 1.146 or something like that. Can the iteration fail sometimes? Absolutely, it can. So we had this one earlier, and it's being rearranged differently. So if we start at this value here, look at what happens. We go vertical, we go horizontal. We go vertical, horizontal, where would we even go? It's so far away we can't see it. So because it looks as though, because we've started on the right-hand side here, and the nature, the shape of that blue line, that seems to have caused our iteration to fail. So there we go. We've talked now about rearranging to get an iterative equation, and we've had a look there at when it works with a staircase and a cobweb, and also when it fails.